asked for. So if we're looking at acids and bases, which we are technically right now, we're using this to kind of leverage your current knowledge or your past knowledge about acids and bases, and to use that to help you figure out how to draw arrows. Right? So first thing I'm going to go through and do is erase the arrow. And we'll come back to it in a second. Erase as much of the arrow as I can. So content that we want to be able to leverage. So the content we're leveraging is what you already know. Define an acid. Okay. H plus donor is our definition of acid. If we reflect all the way back to what you learned in 152, which was just last semester, guys, and since I'm teaching 152 right now and on this topic, I also know that it shows up in the lectures so that I know you've seen this. Right? The definition, at least used in the notes that I'm using for the 152 class, is slightly different. What they're using is it is a species that donates H plus to water. Right? And the reason why we talked about donating H plus to water is a mix of historical kind of reference to the definitions for acids. And what we're trying to reference there is the Arrhenius definition. So when we talk about our Arrhenius definition, it's the production of H3O plus whenever you dissolve the species into water. So they're talking about that chemical reaction. If we switch to outside of water environments, we're still going to talk about H plus. Okay, H plus is being donated to something else. In the Arrhenius definition, it's the formation of H3O plus because our acid donated H plus to water. Right? So we tweak the definition slightly. So it is an H plus donor. What is a base? An H plus acceptor. And if we go back to the Arrhenius definition again, the Arrhenius definition is really focused on water. So a base is when it reacts with water, it increases the concentration of hydroxide ion. Right? Which is fantastic and great if we're in water. We're in freaking organic chemistry. There is no water. Right? So that water definition isn't particularly useful, which is why we do a subtle shift and we bring in this H plus. So we hyper-focus on the atom. Right? So historically, Arrhenius 6, I don't know how long dead that dude was, but long dead. Let's say 600 years ago. We tweaked the definition slightly to look at our Bronsted-Lowry definitions, which is transferring of hydrogen ions. So instead of saying, well, hydroxide or not, we just focus on the H plus atom. Okay? Even that definition is still 200 years old. Okay. What ends up coming in as a new or potentially better definition, and I would argue it's not necessarily better, it's more appropriate, has to do with the intent of these definitions. The intent was to explain chemistry. What chemistry? All chemistry. That was the goal. So when we thought about chemical reactions or what we were exposed to, we noticed lots of acids and bases. So we started with our definition system in that wheelhouse. We then quickly noticed that there's other things going on beyond just the transfer of hydrogen ions. So how can we explain those if this definition doesn't apply very well? Oh, that's just a new definition. And this is where students hate things. Oh, it's an exception. It's not an exception. It's just the initial definition we had wasn't broad enough to react or encompass all chemistry. Lewis, 1913, somewhere around there. Okay. The same Lewis of Lewis dot structures, interestingly enough, went through and said, well, now that we have structures, we can look at what's changing through the course of our reactions. And instead of talking about the hydrogen ion, he shifted his focus to talk about the electrons that are moving around. Because when we talk about the transfer of a hydrogen ion, that's not particularly useful. And that's actually, if we go back to our arrow here, nope, never mind, that arrow isn't showing that. You'll find some Gen Chem textbooks will be like, oh, a hydrogen moved over here. And it makes all organic chemists around the world cringe and get really irritated and frustrated because it's screwing those students up for when they have to advance. Okay? But what they're trying to show is how the hydrogen has changed locations. The problem with that is that atoms change their position in space all the time. Okay? And a connection between things isn't defined based off of proximity. And so the example that I used in lab on Tuesday, okay, my hand is connected to me. But if we look at the distance, we say, oh, well, it's of course, because your hand is close to you, and therefore it is connected to you. Because if we took that hand and I somehow was able to put it by the door and my body stayed here, we'd be like, your hand is no longer connected to you. So we'd say, oh, it's the distance that matters. But if that's true, the closer I walk to Gavin, the more connected we are. And Gavin says, we're not connected. Stop coming near me. Okay? We're not connected. There is still no connection there. Okay? The only way, and even if we shook hands, okay, that's not an actual connection. At no point ever am I going to be physically, I hope, sorry, Gavin, connected to Gavin at any point. Okay? Because that's not a chemical connection. So when we're talking about our chemical reactions, what is causing the chemistry? How do I know that hydrogen has changed its locations? If it's not distance, what am I looking at that says that hydrogen is in a different spot? It's the electrons. The electrons in HF are no longer in that space. They're no longer in the bonding space. They're sitting on the fluorine. And the electrons on the oxygen are no longer just chilling on the oxygen. They're being shared with the hydrogen. So it's the change in the location of where the electrons are that's actually dictating the chemistry. So as soon as we have Lewis structures, we can start to explain this. How do we get Lewis structures? We need to know an electron exists. Okay? Did Bronsted-Lowry know about electrons? No, because electrons were 1890. Okay? So just historically, we didn't have that information for those initial definitions. Okay? So Lewis comes in and says, well, an acid, okay, yes, an acid can go through, and we can talk about the proton donation, but what I can actually talk about is that it's an electron acceptor. Okay? And then the base would be an electron donor. Okay? And the beauty of this new kind of definition set from Lewis is this now applies to all chemical reactions. Right? We go, well, that's great. We've got a definition that applies to everything. The problem with that is that if it applies to everything, it equally applies to nothing. Okay? So while it was a brilliant observation to go through and make, ultimately the Lewis definition is now so broad that it doesn't help us narrow down what chemistry is actually happening. Right? And for that reason, I tend to avoid using the Lewis definition. Right? And tend to center on the Bronsted-Lowry. So that when I go through and talk about acids, I'm very specifically referring to a Bronsted-Lowry acid, not a Lewis acid. And the Bronsted-Lowry acid is talking about the transfer of the hydrogen ion. So it's a change in focus. How we represent that and use arrows is still going to fall back on the Lewis definition, but you're just shifting your focus around to help kind of define the chemical reaction that's happening. Kind of, sort of?
So would like pH more resemble like the Bronsted-Lowry definition?
So pH is ultimately purely, well, it's not even Bronsted-Lowry because pH works only in water. pH, I would argue, actually goes all the way back to Arrhenius. Right? And if you go all the way even back to Arrhenius, you can still apply the Bronsted-Lowry acid definition to the Arrhenius definition. You can still apply the Lewis acid all the way back to Arrhenius. But you can't apply Arrhenius up to Lewis. You can't apply Arrhenius up to Bronsted-Lowry. Okay, so the older definitions tend to be more and more specific, okay, to those scenarios. And so depending on what you're trying to do, you may want to broaden or narrow your field. Okay? So within this section, we're talking about acids and bases. So we're going to ignore Lewis for the moment because your question was, well, how do I represent this? Or not ignore, because the Lewis is telling us how to do this. Bronsted-Lowry tells us we've got these acids and bases. Lewis is now telling us what the electrons are doing. Okay? So we could go back up to our system, or up to our equation. HF is going to be our acid. OH minus is going to be our base. How do we know that? Okay, so we can start to push on some kind of observations. Okay, bases, why would I expect OH minus to be a base? Name a base. NaOH. Na what? Okay, so your general knowledge is already giving you that classification of a base. And if we know that one's a base, the other one needs to be an acid. Okay? Why not look at the acid? Well, to be an acid, what does it need to have? A hydrogen. Which species has a hydrogen?
Both.
They both do, so that becomes a harder one to nail down based off of acids. Okay? Based off of your current knowledge of acids and bases. Okay? So now that we know which one's which, we can now go through and layer in our extra information here. Okay? Typically, it's easier, in my opinion, to reference our bases. Our base needs to be the electron donor. So I'm going to go to my hydroxide, and it needs to donate electrons. What does it need to donate electrons to? It has to donate electrons to the H because our Bronsted-Lowry definition was an H plus acceptor. So what I'm going to do is add a curved arrow to go from the electrons on the oxygen to the hydrogen. Okay? That's all I'm trying to say. Same principle as resonance, except now we're actually moving non-bonding pairs to an atom, and we've never really done that. And that's because this is a chemical reaction. The next thing that I kind of want to push in on is I want you to be able to draw the result of that single arrow push. Draw what that means. Literally, like right now, draw it out. What would your resulting structure look like? There are no more arrows. Okay? And I understand where you're going with wanting to draw more arrows. I don't care about more arrows. All I care about is draw exactly what those instructions tell me to do. That's what you need to get. So let's talk through this. There are actually going to be a couple of interpretations that come out of this. Okay? Formally, all of those interpretations are wrong. Okay? But what we need to do is discuss why those interpretations are wrong. So first and foremost, the one that I saw most frequently was this. And we'll kind of color code on this. H and then F. Right? What are you saying that arrow did? That arrow is now saying the transfer of electrons from one atom to another. Our arrows don't get to do that. Okay? Which becomes complicated if we talk about redox reactions. Because curved arrows don't do a good job of explaining redox reactions, because redox reactions talk about the actual transfer of electrons from one atom to another. We're not doing that here. What that arrow is showing is how I am sharing or unsharing electrons. And in this case, I'm talking about how that oxygen is sharing electrons with hydrogen. And if I share electrons with that hydrogen, what should be my new drawing? A bond. Okay? So the first representation we did changed the meaning of our electrons, or our arrows. Our arrows are just talking about sharing electrons. Okay, that's ultimately it. Sharing or unsharing. You switched it, and understandably switched it. Admittedly, I didn't think of that as a possible answer choice, but you switched it to the transfer of electrons. We don't transfer, we share or unshare. Okay? So if it's a share, I create a bond. That's what that single arrow means. I have created that bond. Okay? Now that I've moved some electrons around, I need to evaluate. Is this a good structure? No, why not? Okay. Hydrogen can only have 2 electrons around it, and it currently has 4. That's a problem. Okay, so this is technically an invalid structure. But just like we did with resonance, we can use this to help us figure out what we want to do. So we look at our exceeded octet. This is bad, and therefore it doesn't exist, so we're going to have to erase it. But we can use this to help us think through what has to happen. When we did resonance and we drew that bad structure that we exceeded an octet on, we looked at it and we said, how could I fix it? And the how we could fix it with resonance was do what? Move a pi bond. And if we had more than one pi bond in that drawing, that meant we could move on to a different resonance structure. If we only had the one pi bond that we just made, we go backwards and there was no resonance. So we look at this structure. Now it's not going to be about pi bonds. Why? Because it isn't resonance. This is talking about chemical reactions. And in chemical reactions, we can break sigma bonds. So what we're going to do is look at this bad structure and say, is there a bond that I can break? Well, it's got 2 bonds. I can pick either one of those bonds and break it. The question becomes, which bond do I break? If I don't like that red one, what do I have to do? Well, the exceeded octet on that hydrogen is the problem. I would have to move those electrons back to the oxygen. I'd be adding that arrow to a structure I'm not allowed to draw, which means I would then have to go back to my original and say, put the electrons back, which ultimately means what would my result look like? The exact same thing. Nothing changed. So really what we're saying is no chemical reaction. Okay, so that is one possible way that we could fix that bad octet. What is the other way we could fix it?
Move its other bond.
Move the other bond. And I want to move that bond away from the problem. The problem was the hydrogen exceeded the octet, so I want to move those electrons to the fluorine. Okay? But I'm adding that arrow on a drawing that I'm not allowed to draw, which means I have to take that arrow and put it right back on the valid drawing. I have to go over here. How does that change my answer? Now draw the result of that arrow pushing. Hopefully, you would get something that looks like this. All right. I attempted to color code, and I think I did a horrible job of it, but close enough. Okay. Have I drawn appropriate Lewis structures? Okay. My octets are fine, so that's good, but I do have to resolve, do I have any charges? Okay, so I could go through and I should evaluate the atoms that had anything changing to them. Did the first hydrogen on the left have anything change to it? Nope, so I don't have to evaluate it. How about the oxygen? Did anything change to it? Yes, so I should evaluate its change. Okay, how do I calculate formal charge? Valence electrons. Oxygen has 6. Minus the 4 non-bonding electrons. Minus the 2 bonds gets me 0. Or, yes, how else would I figure out it was neutral?
It looks symmetric.
You memorized the common bonding patterns that you were told to memorize in Unit 1. If you had those memorized, ta-da, it's 0. I know that because I have oxygen with 2 non-bonding and 2 bonds. How else? Oxygen is negatively charged. What does this arrow show? Okay. Sharing of electrons, meaning it's losing an electron. And if I'm negative and I lose an electron, I become neutral. Ta-da! So I can use the arrows to help me predict what's going on with the charges as well. That's kind of neat. Okay, what happened to the hydrogen? Started neutral, and the first arrow shows electrons being shared with it, which means Negative. The next arrow means it lost electrons. And if it has both gained and lost electrons, what happens to its charge? Nothing. It stays the same, so it stays neutral. What happens to the fluorine? It should be negative because it has gained electrons through the course of that reaction. And what have we now done? We've added curved arrows and predicted products to explain this chemical reaction. Kind of make sense? That's all you're trying to do at this point. Okay, so the acid-base thing is, what do you know already about acids and bases? Let's leverage some of that content. Realize that it's talking about atom motion, and atoms don't move, okay? At least not moving in a way that would cause bonds to change. Electrons are the things we have to focus on. This is why we talk about molecular orbital theory and all that fun stuff. Okay? So let's now look at how the electrons move. And as soon as I start talking about electrons, now I can start showing those curved arrows, because those curved arrows are exactly what we did when we talked about resonance. And I now have a way to show how I move from one reactant set to a product set with the use of those curved arrows. Kind of make sense?
Could you do another one?
Sure.
On my smart.
Yes, but not yet. So I'm going to do another one. And this should be a little bit more challenging because we're saying, oh, let's just leverage all the stuff we already know. Okay, do we see an acid? Yeah, to be an acid, what do we need? Hydrogen. Cool. Where do you see a hydrogen?
At the ends of the carbons.
Cool, at the ends of the carbons. Okay, so what could happen? Say again? One of what? You mean the hydrogen's going to move?
No, the electrons on the hydrogen are the electrons, period, are going to be shared with the fluorine.
Does the hydrogen have any electrons?
So you're going to take the
Okay, so this is part of this because we heard a statement. Oh, let's take the electrons and we'll share them with the chlorine. Go back to our definitions. Okay, our base must accept hydrogen by doing what? Donating electrons. So if you're saying the hydrogen needs to end up with the chlorine, I know where you're going. You're saying, oh, that's the first one's the acid, the other one's the base, and what you're trying to go through and describe is how we're transferring the atom. Atoms don't move. I can't use an arrow to show atom motion. That doesn't happen. What moves? Electrons. So you said, oh, well, it's hydrogen needs to move, so I'm going to take the electrons that hydrogen's next to. Does the acid move electrons? Okay. And if you're like, well, I don't remember the Lewis definition, that's okay, that's fine. Acids donate what? H plus. How many electrons does H plus have? 0. Acids don't have electrons to move. So I don't want to use that arrow in purple. I want to do something else. This is where I can shift to my Lewis definition, and again, I would lean into the base. Okay? The base must act as an electron donor. To act as an electron donor, what should it do? Donate electrons. So I'm going to start an arrow where I have electrons, the negative charge, and I want to share them with And for those people watching at home being like, why did you just draw this weird bumpy thing? That's because people went through and told me to share with carbon. Oh, okay. So what you were saying was an entirely different statement. You went through and you shared them with the carbon. Okay? That's actually why I drew this, and then you all mentioned the hydrogens on the carbons that I forgot were present, which was going to cause me to do a whole different shift. So you're now saying that this is our result, right? Everybody okay with that?
Are you okay with that?
I'm actually okay with it. That's where I wanted you to go first, and then you all did something else, and we'll come back to the something else because it's also equally valid. Is everybody okay with that? Everybody understand what we just did? Why did we go from the negative chloride to the positive carbon and not to the hydrogen? There's a greater attraction between the negative and the positive. So what you're doing is reacting the most reactive things. Awesome! That brings that negative and positive together, which then produces this product, which is fantastic. I love it. Did you do an acid-base reaction? No. Because an acid-base reaction, again, remember our context of it, an acid-base reaction is transfer of hydrogen ions. Did you transfer hydrogen ions? Nope. So this isn't acid-base. Does it fit the Lewis definition?
Yes.
It does. Okay? The chloride acts as a Lewis base by donating electrons to the carbon structure that acts as a Lewis acid by accepting those electrons. That's all perfectly fine and dandy. But if I start going through and calling this Lewis acid base, you're going to hear acids and bases, not Lewis, and shit explodes. Okay? So I want to be able to reference these with another word because I want to point out that this isn't an acid-base reaction. I want to have a different set of language to explain those other types of chemical reactions. Okay? This again comes back to the fact that Lewis is too broad a definition. So when we talk about the transfer of electrons not with H+, we want a new description. That new description becomes nucleophiles and electrophiles. Okay? And everybody freaks out and says those are stupid. Those are better than acids and bases. What part of the word acid tells you donates H+? No part of the word. Look at electrophile. What does phile mean? Likes. What does electro mean? Electrons. And what are electrons? Negatively charged. Okay? An electrophile is something that likes electrons. This positive species liked electrons, which is why electrons went to it. That's now an electrophile. What did the other species do? It was a nucleophile. Because what did it like? Nuclei. And what's in the nuclei? Positives. The nucleophile electrophile definitions can now apply to anything that is not acid-base chemistry. And our acid-base definitions will now apply only to acids and bases. That can make life a little bit easier when we talk about naming how each of our chemicals are reacting. Instead of having to go through and say chloride or tert-butyl cation, I don't have to do nomenclature, organic nomenclature. I can just categorize how that functional group reacts or how that structure reacts. Kind of make sense? Okay. Could those two structures still act as acids and bases? This becomes a fun one. Yeah. Yeah, they could. So let's get rid of those definitions, which I'm probably going to regret here in a second, but whatever. Life's full of regrets. That shouldn't be that color. Let's have our base, the chloride, share electrons with the hydrogen. What happens? The resulting electron, or the resulting structure, should show an exceeded octet on the hydrogen, which means we have a bad drawing. We'd have to fix it by adding an extra arrow. Okay? So what we could do is add an arrow to put those electrons on that carbon. Identical to the OH minus and the HF reaction we just did. Everybody okay with that? What would the resulting structure look like? Good prediction, but slow it. Okay? That's all that would happen. Ta-da, there it is. But you said form a double bond. What do you mean?
The electron, that.
Through a process known as? Through a process known as resonance. Okay? Which is then going to bring in a whole nother level of crap that we have to worry about. As we've drawn it in black, what chemical reaction happened? Acid base. All we did was transfer a hydrogen from the carbon structure to the chloride. But if we look beginning to end, our black structure at the beginning to the green structure, what chemical reaction did we run? It's an elimination. It's an elimination because we formed a pi bond. But Gavin said it was acid-base. Okay? And this does create a bit of a dilemma within our systems. When we talk about our chemical reactions, we need to be a little bit more nuanced with our mechanisms. Within our mechanisms, we need to draw the most stable products each and every single time as we progress through. This becomes increasingly an issue in second semester. First semester, it's relatively minor. This is the first place that it would potentially show up. What do I mean by that? This middle black structure, is that the most stable structure? No, it's not, which means I shouldn't have drawn that as my product. What should I have drawn as my product? I should have drawn the green structure. But my arrows took me to the black structure, which means my arrows are incorrect. How do I fix them?
Just run it to the bottom.
I will take those electrons from that bond, the exceeded octet on that hydrogen, and instead of moving them to the carbon atom, I'm going to move them to the bond. That is going to bypass that middle structure and take me immediately to that resulting thing. I still know that there's resonance, and I can think about that if I really wanted to, but that sets me up with a smoother mechanism that gets me to the most stable product as quick as possible. If we now go through and try to label things, what did the chloride act as? What did it do? It acted as a base. It accepted a hydrogen. What did the other structure do? It lost its hydrogen, therefore it acted as an acid. And this chemical reaction would be called elimination. But it was an acid and a base. The acid-base reaction definition says the only thing that can happen is the transfer of a hydrogen. Is that the only thing we did here? No, we also formed a pi bond. Is that sneaky and underhanded? Potentially, but it helps to clarify the language with how we navigate and classify chemical reactions. Okay? So there is an overlap that is potentially confusing. We have to watch out for the overlap in those definitions.
So would the leaving group be the hydrogen at this point?
Okay, which then brings in a different level, because if we push all the way into the definition of the elimination also has a leaving group. Okay? when we talk about eliminations, we're talking about them as reactions. This is not technically a reaction. Then what the hell is it if it's not a reaction? It's a mechanistic step. And if I wanted to see what the reaction was, I would have to go back to where this molecule came from. How do I know this molecule didn't just exist? Because it's a cation, and cations are not stable on their own. It had to have come from somewhere. And if I look at the from somewhere where it came from, it had a leaving group on it. Right? So we now run into an extra layer of crap that we have to nuance between this. Not only do we have what are these classifications of what the reagents are, acid base, or if we try and tie that together, acid base, electrophile, nucleophile. I also have to be able to classify the overall reaction, but the overall reaction will break down into individual mechanistic steps. Like, God, this is too much stuff to learn. You already knew that. No, I didn't. Yes, you did. You learned it in 152 when you talked about kinetics. Because when we looked at kinetics, you had an overall reaction, and then that reaction broke down into elementary mechanistic steps, of which you were only concerned about the slow step to determine the rate law for that overall reaction. Ta-da! 152 comes back and kicks you in the ass. It's always 152's fault.
So each
Hate that class.
step within a reaction is an elementary step, and then the arrows in itself.
Each
are
mechanistic step is an elementary mechanistic step, yes. And it can break down into acids and bases as labels. That doesn't change kind of the definition behind it. So if we now want to layer in formally, we're trying to say it was an elimination reaction. What specific mechanistic step did we undergo?
maybe.
Okay. That, again, becomes a harder question to neutralize or figure out what's going on within that. This was the loss of that H plus and the formation of the pi bond. This is an electrophile elimination. Yes. Okay? And if you're like, dude, there's so many terms floating out there. Yes, this is why you should have hopefully already watched how do we classify reactivity, because that layers in our information about what our reactions are, and all the mechanistic steps, so that you're seeing all these pieces. Okay? One of the questions that very quickly comes up very early on is, how do I know, or why does it do this? Don't worry about it. You don't need to know why any of the elementary mechanistic steps do anything. You just need to know that it is an elementary mechanistic step. These are the curved arrows that describe what's happening within it. These are the overarching pieces that I would expect to see. When do you need to know why and how it is doing it? When we talk specifically about the reagents that cause that mechanistic step. Okay? That's when it becomes important. Okay? So the electrophile elimination, that's going to become important. You will need, by the end of these next 4 weeks, to know why it's happening. Okay? Nucleophile elimination, you don't care about till second semester. You don't need second semester, you don't care about it at all. Well, you care about it a little bit. You need to be able to identify it. Okay? But you don't need to know why at all. The point of that chapter 7 is to set you up with, here's all the pieces. Now that you know what the pieces are, let's talk about why and how they work and how they interplay with each other. Okay? So your chapter 7 homework isn't about why, it is. And within that it is, there's a couple different places to go. You get the question of reactant and product. Okay? It is what? Would I expect this to be a substitution mechanism? Okay? Is this SN2? Is this coordination? Is this electrophile elimination? Yeah, it was electrophile elimination. Well, I remember you just said that, Mike. Yes, ta-da. Because you can look at the changes from reactant to product to identify that. Okay? We could also go through and give you just the reactant and the curved arrows, and you have to tell me what mechanism it is. Why don't I give you the product?
So it'd be too easy.
Technically, I already did. I gave you the instructions to be able to tell me what the product was. So if you need to draw the product for your sake, draw it. If not, identify it from the curved arrows with that starting material. That's what Chapter 7 homework is having you do. Look at each of those pieces and say, this is what it is. Okay? We could also go through and say, this is a coordination. Predict the products. If this is a coordination mechanism, what does that mean? That means the negative shares with the positive, and I get that. That's what that means. So what you're trying to go through and do is work through the meaning of those words, the meaning of those arrows, the meaning of those structures back to what those words are. Okay? Again, why? Because it can help to classify the potential hundreds of reagents that you will learn by the end of second semester. Okay? And if you don't have a way to organize those pieces of information, you're trying to file through hundreds of different things at once to predict reactions. That's not easy to do. This is trying to help you build the skeleton structure so that you can start classifying those reagents. Kind of, sort of? Okay. I think we flogged that one to death. You happy enough with that? Okay, you said you wanted another one? So I would complain a little bit here, and I'm going to complain a little bit because I don't think what you drew is what your arrows show.
It's like it's opposite.
So what? Is it?
Yeah.
You're right. Good job. Yeah. So what you drew is exactly what your arrows show. Hell yeah, that's awesome. I can't give you points, but good job. Right? It's not what the question asked for, but it's fantastic. That is absolutely lovely, and that's awesome, right track to be doing. Okay? So what we want to lean into a little bit here, okay, is we need to leverage some information. Okay, that some information we need to leverage is forget all the stuff that I just spent 43 minutes talking about. What was this chapter? Acids and bases. Okay, and if we're talking about acids and bases, we're very specifically referring to Bronsted-Lowry. And a Bronsted-Lowry acid is a H plus donor, and a Bronsted-Lowry base is an H plus acceptor. Okay, and you just dropped an O on this, which is fantastic, because what did you do?
I just have one final product instead of two.
No,
Is it supposed to be H?
there's also going to be that too.
Oh, really? Then I don't know. You just wrote a base. Just a base.
You're talking about this structure having gained an hydrogen, right? Did it gain H plus? No, it gained H minus. That's not an acid. The reaction you ran isn't Bronsted-Lowry acid base. Okay? And this does become tricky with reagent sodium hydride. Is we see H and we go, oh, we're putting H on, it must be acid base. No, it's H minus. Because it's H minus, you're not in Bronsted-Lowry terms.
Are we adding an H to the hydro? The negative H?
We need to use that negative H to do something. The question becomes is what do we use that negative H to do? I don't know if they gave you the lone pairs. If they didn't, good job including them. Okay? We got that negative charge. Okay? We need to figure out which species is which. Okay? So we want to try and find an acid or a base. Can H minus be the acid? It needs to have an H, but the H must be positive. So H minus cannot be the acid. H minus must be the base. Which means what's the other species? The acid. So one of those hydrogens is H plus. Which one? Doesn't matter because of symmetry in the molecule. Awesome answer. Okay? So I'm going to pick the one on the right because that just happens to be closest to where my H minus is. Okay, so if I'm going to describe mechanistically what's going on, we're going to take the electrons from my base, my H minus, and I'm going to share them with the hydrogen of my acid. This would exceed the octet on that central hydrogen. Okay, or we'll call it my purple hydrogen. Okay, so I don't even want to draw it out to see that. If you don't see that we've exceeded the octet with that arrow, you need to draw it out. What needs to happen? I need to take the electrons in that bond, and I need to move them. Where can I move them? To the carbon. That would be my curved arrows. What happened to the hydrogen on the left? Nothing. What happened to that carbon? Nothing. What happened to the triple bond? Nothing. So all of those stay constant. That last carbon gains a pair of electrons, so we'll show that as a non-bonding pair. I've got my purple hydrogen. We're trying to show it distance-wise. It's about the same distance. Okay? And then I have a bond, more or less, to that hydrogen. So far, so good? Okay. Now we encounter the last step of this. We have to make sure that we've accounted for charge appropriately. If you know your common bonding patterns, boom, done. Okay. If you want to calculate valence electrons, you can calculate all and do all that valence electrons count if you want. Okay. Or you could follow your arrows. Okay. The negative hydrogen shared electrons, so it lost an electron, which means it's going to become neutral. That purple hydrogen gained electrons and lost electrons, therefore nothing happens to it. It stays the same charge. The carbon gained electrons, which means it therefore is negative. And what I've now drawn is the product of that arrow pushing. Make sense? Which then sets us up with part 2. And part 2 asked equilibrium, because 152, which way does this reaction favor? Okay, what we did is said, let's just say it happens. Ta-da! This is what it would get. Okay, should it favor the products, or should it favor the reactants? This is getting into the how and why question. And if you're like, but Mike, you said no hows and whys. I said no hows and whys unless we were talking about the specific reaction. Chapter 6 is all about acids and bases. We're talking specifically about the acid-base reaction, which means you need the how and why. Okay? We could try to leverage content that you theoretically already know. If we're talking 152 dynamics, how do we know which way the reaction favors? What's that?
More stable.
Okay, more stable. We could look at conjugate or pKa's. We could look at Ka expressions, so we'd have to look up K's for each of these things. And if we're going to talk about Ka's, we could look up the Ka for our acids. Okay, so we've got the Ka for our first species up here, comes in at 25. And then we go over to the other side, we have to label the acids and bases over there. Which one's the acid? Negative carbon or the H2? HH is our acid. And if we look at its Ka, it's something on the order of like 60. And for you being like, how do you freaking know that? Don't look up the Ka for H2. I don't actually know that one. I do know the one for the first one, and that is one you should probably memorize, and 25 is ballpark. I think it's 25 to 27. Right? What does it mean if we know those Kas? What's that? And this becomes the kind of shitty, unfortunate thing that goes with this. Okay? One's bigger, one's smaller. What does a bigger or smaller pKa mean?
Smaller pKa means stronger acid.
Smaller pKa means stronger acid. Okay? And if you struggle to remember that, I can tell you what I would go through and do, which is painful. Okay? But you should get used to it by now. I would go through and say, well, Ka is A minus times the H plus over the HA. So if I had a big Ka, lots of this, okay, so a number that was a lot bigger than 1, what would that mean for a pKa? Logs? I don't know how to do logs in my head. So I'd pull out a calculator and I'd say negative log 100. What's my number? Oh, it came out to be a really small number. What does that mean? Small numbers are strong acids. Okay? For those of you that are more math inclined, you could probably do that all in your head. Or those of you that have memorized it, okay, probably the better option, because I'll admit the derivation process is a bit tedious. Okay? And for me personally, it requires a calculator, because I'm an idiot. Kind of, sort of? You're not supposed to shake your head at that. It's just rude. Okay, so cool. What do we decide? 25 is a stronger acid. What does that mean?
It will dissociate. We'll go that way.
Go out the door?
We'll go that way.
Okay. The equilibrium is going to favor the products. Okay, when we run a chemical reaction, our products are always lower in energy than our reactants. That's how it works. Okay. Well, what about endothermic reactions? Endothermic reactions throw in another little kink behind it, and we tend to ignore some of the pieces that associate with that. To get an endothermic reaction to happen, you typically have to add an extra amount of heat or energy or other thing to force that reaction to go through and happen. Our acid-base reactions are exothermic. They will always trend to the weaker acid. Okay? So that required you knew the pKa's. Did you know the pKa's? No, so you're shafted. Okay, because you can't look up the pKa's on the exam unless you've bothered to memorize them. Okay, so how else can you do it?
Stability.
Stability of what?
Product. Or both. The acid and the conjugate base.
Okay, and stability, absolutely is the right idea, but now we have to figure out what stability thing we're going to go through and rank. Okay, what is organic chemistry all about?
Electrons.
Hell, electrons, yes. Okay, so if I'm concerned about stability, the thing that I'm concerned about is where are the electrons. So if I look at the reactants, where are the electrons? On the hydrogen. That's H minus. If I look at the product, where are the electrons? On that carbon structure. Okay? The electrons are easiest for me to manipulate because my entire course thought design is how do electrons navigate and move. So let's look at where the electrons are located. And we're going to compare those two species. And if we're going to compare those two species, it might be nice to have a name to them. That would be the base and the conjugate base are going to be the two things we're going to compare. Ultimately, we're just comparing the bases across the chemical reaction. How do we go through and compare them? Close. First, we would compare them based off of the charge. Well, hydrogen is a negative charge. Carbon is a negative charge, which means, is there a difference in charge?
No.
Nope. So what do I move to?
Size.
Size. Is there a difference in size between carbon and hydrogen?
Yes.
Yeah, different rows. Okay, different rows. What's that difference in size? I don't care about significant. Is hydrogen bigger or smaller than carbon? Okay, hydrogen is smaller. What does that mean to the stability to stabilize the negative charge?
It's higher. Sees less area.
Okay. So if we look at hydrogen, ta-da, there's hydrogen. We look at carbon, ta-da, there's carbon. Each of them have an electron. Boom. Boom. The electron's the exact same size. Okay? And if we want to consider stability, this is how I like to think about size, for the record. We want to think about stability. If that electron touches anything, chemical reaction. Okay? And so let's envision it that if we touch that electron, that's a chemical reaction with us, but let's make it more exciting. Okay, you get a little buzz, shock, like sticking a fork in an electrical outlet. Okay? So you've got those two circles to stick your hand into. Which one do you prefer to stick your hand into? Okay? The top one or the bottom one? The bottom one. Why? There's more chance of not getting shocked. You mean not having a chemical reaction? Why? Because it's more stable. Go back to the prison analogies that we've used as well. Okay? When we penalize people, where do we put them? In a small 10 by 10 box, and 10 by 10 is probably generous, 5 by 5 box. Okay? And when they're done with prison, what do we do to make them feel better? We take them out of the box, and they have freedom of the whole world again. Okay? That's got to mess with your brain a whole lot. Okay? That's the exact same thing that's happening here. Okay? Small little box, that's very reactive. Big box, freedom and stability. What does that mean for us? Which one of these is more stable? The products are more stable. And since the products are more stable, which way does the reaction go? Favors the products. So I don't have to know anything about pKa's if I've remembered how to rank my stabilities. Okay? That's where I start with charge. I move to size. I look at electronegativity. I look at resonance. I look at induction. And then I hope and pray that I never have to answer it. Okay? That's the sequence that you should kind of navigate through. That sequence should be at the back of your mind for every single reaction you do. Because it applies to every single one. Okay? Kind of sort of makes sense? Should we make it more challenging? Did you say no? Sorry. I'll apologize to you. What if I make it NH2 minus? Okay. Theoretically, we're a little bit better than showing it as NH2 minus, but you should be able to predict what NH2 minus means. What does NH2 minus mean?
NH2 has a lone pair
True, where's the lone pair?
on the nitrogen.
Okay. NH2 minus hopefully gets you to this structure relatively quickly with a lone pair on the nitrogen. Okay. Which then means when we go through and run this acid-base reaction, we're going to be adding that hydrogen to our nitrogen, and we're going to have that lone pair. Everybody good so far? Okay. So really, what did we change about the acid-base reaction? Nothing. Right? And that's the beauty of knowing the pattern of your chemical reactions. I can swap in whatever I want for each of those individual reagents, and it has no effect on the core functionality of the chemistry. You have to keep your focus where the chemistry is located. The rest is a distractor sometimes. Most of the time, I should say. Right? But now let's move, because I said this was a harder question, and so far we didn't change anything about it. Now let's move to looking at which way does the reaction favor. Okay? So you've immediately jumped on reactants. Why did you immediately say reactants are more stable? Okay, awesome. I like that. So you immediately jumped. You had to backtrack a little bit. Okay? We start with charge. So you're jumping and you're immediately starting with looking at stability because you decided you didn't memorize pKa's. Good, most people didn't. Okay, so we'd go through, we have negative carbon, negative nitrogen. They have the same charge, no difference. We move to the next rule, which is size, no difference. And you're like, oh, never mind. There's more after that. What comes after size? Electronegativity. Cool. Is there an electronegativity difference between nitrogen and carbon?
Yes.
Yeah. What does that mean? Nitrogen holds its electrons better, which means
It's more stable.
it's more stable, which means
Favors reactants.
favors the reactants. Everybody happy with that? You're ready for the shoe to drop, right? Okay. When you looked at the electronegativity difference between the nitrogen and the carbon, what was the hybridization of your carbon? When you looked at the electronegativity difference between carbon and nitrogen, what was the hybridization of the carbon? And for people looking at the screen says nothing about electronegativity. Where did you pull your electronegativity information from? The periodic table. What was the hybridization of carbon on the periodic table?
2.5. Hybridization. Or hybridization.
So even asking the question, what do you mean hybridization? Yeah, because it's not. When we look at our electronegativity differences, okay, and we talk about them from our periodic table, we are ranking them based off of their atomic state, their non-hybridized form. Does hybridization have an electronegativity effect? And you're like, I don't remember. Maybe the way you're saying that makes me think it does, but you definitely didn't tell me that. Go back and rewatch the hybridization lecture from Unit 1, and we explicitly talk about why it is important to know about hybridization, because hybridization absolutely modifies your electronegativity, which means the electronegativity trends that we have memorized or used from the periodic table are really only applicable when I'm comparing equally hybridized elements. Is the carbon and the nitrogen equally hybridized here? No. Which means trying to use the trends of electronegativity are going to become really challenging to manipulate. Because as we decrease decrease hybridization, we increase electronegativity. That becomes problematic because our carbon is very much unhybridized here, or very close to unhybridized, whereas the nitrogen is very hybridized. So the nitrogen's hybridization is causing its electronegativity to go up, and the carbon's is causing its electronegativity, the nitrogen's hybridization is causing electronegativity to go down, and the carbon's hybridization is causing its electronegativity to go up. That becomes a problem because of where nitrogen and carbon are as far as electronegativity on the periodic table. They're really darn close to each other, which means a subtle change in that hybridization can have a wild effect on the end result. Okay? Which means the rules of thumb for determining reactivity, charge, size, electronegativity, resonance, induction, and all that fun jazz, don't work. How do we get around it? When a rule of thumb doesn't work, the way you get around it is by memorization. That's it. How you decide and what you decide to memorize is ultimately going to be up to you. Typically, when we talk about this very particular example, the triple bond, the terminal triple bond, right? To remove that hydrogen, sodium amide is the weakest strong base to remove that hydrogen. So sodium hydroxide won't do it. Sodium amide will. Sodium hydride is a stronger base than sodium amide. Why? Size. Right? So if we're going to run a reaction where I need to remove a hydrogen from a triple bond, what I'm going to memorize? Sodium amide. Okay? Now I know anytime I see a triple bond with a hydrogen and I want to remove it, I'm going to look for sodium amide. Do I have a base that is at least as strong as that? Yes? Done. That's my answer. Okay? That's a real narrow thing to memorize. Okay? That could be useful. The other thing that I could go through and do, as we already started to allude to, was I had some of the pKa's memorized. If you have your pKa's for your functional groups memorized, you have an out. The pKa for the alkyne, that terminal alkyne, is about 25. The pKa for the amine comes in about 35. Which way does it favor? Towards the weaker acid, and it heavily favors the products. Okay? Which I know is fully, oh, there's a rule, there's always an exception to a rule. There aren't rules, number one. Okay? What they are is generalized patterns that we've been able to apply to these systems. Okay? Patterns will always break. Look at ionization trends. They break. Okay? There's an underlying meaning that we just don't have to put in a simple description that allows us to be able to predict it easily. That's science. Okay? This does not mean you should just give up and memorize everything, because it won't work. Right? But it also doesn't work to just apply, because the application will absolutely fall apart in certain circumstances, and the alkyne is a crystal clear example of where it falls apart. Good question. Any questions about that? Okay. I guarantee you this will show up. Guarantee it. It'll show up. If not on this next test, it'll show up on the final. And if not on the final, it'll show up once or twice next semester. Okay. Sodium amide is a very common, strong base, and it takes it to the next level beyond sodium hydroxide. Sodium hydroxide just isn't good enough when we move into organic chemistry for a lot of our chemical reactions, so we level it up to sodium amide. Sodium hydride takes it a whole nother level up, but it adds the added complication of producing hydrogen gas, and if you're doing an exothermic reaction in the presence of hydrogen gas, that's typically an explosion.
Sodium amide, is that?
So just dealing with the name. Sodium
Yeah.
amide. NH2
Oh,
minus
okay.
is an
Talking about
amide.
The sodium that's leaving. Okay.
Okay, which
So what was the hydrogen beforehand?
that was just sodium hydride.
Oh, okay.
Yeah, there you're using Gen Chem nomenclature.
And is there a table for the pKa's for
Yeah,
the functional groups?
yeah. There's tons of them all over the place. Yeah.
All right. They're all different.
Okay. What you should be looking for is as condensed as possible your functional groups with their pKa's, right? Because you don't want to be looking up the thioester pKa, because that's not going to be relevant. What you're concerned about first and foremost is the functional groups I told you that you needed to have memorized, and the pKa's associated with those, which I believe is actually in the lectures, but I could be wrong on that. That might be something I threw into second semester and not first semester, which would be really rude. But
All right.
is that an exciting place to end?
It's over.
It's only just starting.